All right, recording is rolling. Welcome to Friday, October 27th. So we're going to do a few review things from yesterday. Take us probably 5 or 10 minutes. Main thing today is going to be this Pendulum Speed Lab where we're getting towards the end of class yesterday. Right? Oh, AP guys, what's due Monday morning when you guys walk in on Monday? Yeah, multiple choice questions for Unit 4. Right. I reviewed all the questions. I'm pretty sure you guys should be able to get those right. Yeah, AP Classroom. AP Classroom. Yeah. Yeah, I checked a couple of guys already did it, so awesome if you did. Yeah, you guys remember those 12-row energy tables we've been doing the last couple of days? I did get those checked off, points in the grade book, and they are back on your return folder. So if you wanted those, because might be pretty good notes too, right? All right, so let's do a few review posters before we get to the lab today. All right, one is here's a new concept I had yesterday, so I went home and typed up this poster. New poster, look at that, new poster, yay! So if you see something like an elevator being lifted, that's a particularly opportune scenario for a question like this, like power, right? So that could be work per time, right? Like a rate of energy transfer or rate of work, right? That's usually how it's defined. And then yesterday I said, well, you could break work down to force resistance, and then you could group these variables together differently. You could get this alternate form, right? And that one you'll want to memorize because it's not given to you in AP equations. But I have seen AP ask questions in the past where if you have this memorized, you can answer the multiple choice question in like 5 seconds, right? So that one, good to know. There's an elevator we pull up at some speed. Right? Actually, to add on to this a little bit, if the elevator is accelerating, then the speed is not constant, which means the power would also not be constant. So if you have an accelerating situation, then this would be the power like at a particular instant, but that would always change. And I've seen that question be asked too. So next poster, I don't want to reveal the whole thing, but I'm going to cover part of this up. Do you guys remember, well, here, you guys see the picture real fast. You guys remember the loop of death? There was that bowling ball that rolled down. There was that guy sitting here with the helmet right, running around. I say, well, there has to be like some minimum speed to get around, which is a question that we answered a couple weeks back, right? Which is this right here. And then you can backtrack one more step, and that's to where we're getting to this energy section. Like, how high do you have to drop the ball from? What's the minimum height? So let's go over this. So, first of all, what's the minimum speed to get around? Now, this should be a review question from last unit. Here's the setup. So at the very top, there could possibly be two forces on the coaster at the very top. Guys, what are the two forces? Yeah, the weight mg and also the normal force from the track. Right. Now, if you're looking for like a minimum speed where it just barely gets around, then one of those forces goes to zero. Which force goes to zero? Yeah, the normal force from the track, right? And by the way, both those forces would be pushing down on this coaster cart, right? But yeah, we're going to take the normal force and let go to zero so that we can get specifically the minimum speed, right? And the last step would be, I didn't put the last step, but it would be the square root of that, right? Just square root GR, right? But if you pick up from v squared, that's actually makes a easy substitute for this next section, right? So the next question is, what minimum height do you have to drop this from? And there is an answer in terms of the radial size of the circle, right? There's an answer, right? Oh, you know what, too? Here, do you guys see? This is a side thought. This is fun to think about. I mean, always little fun corners so we can navigate this class. You guys see how it goes down and then like bam goes straight to a circle, and I have a loop that's like pretty dang circular, right? You guys see that circular, right? If you look at the first roller coasters that were made, say like about 100 years ago or so, right, they did look like this. It's like you go from a straight part of the track straight to a circular part of the track, right? But you don't see coasters like that anymore. If you guys ever seen coasters around, ridden coasters, they always look like these teardrop shapes, don't they? They don't actually look like circles. Okay? Now, circles is a simplified form for like good textbook physics, right? But there's a reason that they don't actually build coasters in perfect circles. Do you guys know why? Can you guys think of why? Why would you want a teardrop shape instead of a circle?
So it accelerates down faster.
It has to do with acceleration. Acceleration. Yeah, because guys, if you're in a circular pattern, what kind of acceleration is that called? Starts with the C. Centripetal. Right. Maybe some of those others could also apply, but yeah, look for centripetal force, right? Okay. Guys, if you're in a straight part of the track, and then all of a sudden you hit the circle, bam. Do you guys think you would feel just like regular forces like sitting in your desk right now or riding a car, and then all of a sudden, bam, like the huge normal force pops up as a centripetal force? It would be really jarring, wouldn't it? It's like nothing, and then bam, suddenly you're in a circle, right? Right. So yeah, that is really jarring, and it for both the passengers, but also the track itself, right? It's just like a force just bam out of nowhere, right? So that's why you want a teardrop shape, because it's like a gradual buildup, so that if you're riding the coaster, you can feel the forces start to build up. Right?
Oh, okay.
Yeah,
That way
yeah, right.
people
That might be a reason too. Yeah, maybe you have to hire less custodial staff, right? Yeah. And also fewer medical injuries. Yeah, I guess rank the importance of those. Let's go to conservation of energy. We're going to use to answer this question. What does this height have to be in terms of the radial size? Well, I guess this would be the radial size, right? So the total height of this loop would be 2 times the radius. Right? Okay. So could you guys figure out what conservation of energy setup would that be? Are we going from this point A to this point B? You guys, what kind of energy at point A up here? Yeah, it's all MGH, isn't it? Let's reveal a little bit at a time. So it goes, starts out as MGH, right? And then by the time you get to this point on the track, right? Well, if you define height 0 is down here, then it does have a height. Does it have height 2r? So it's like speeding up on the way down, and then kind of slow down on the way up. Okay. Oh, also, it has to have what kind of energy? Kinetic. Because it has to have some speed. In fact, it has to have this minimum speed. Better have some kinetic, right? So it's a combination of the potential plus kinetic, where the height for the potential is 2r, right? It's playing down. This is the ground level down here, right? Okay. Oh, but look at this v squared. That is, we have an expression in terms of the radius also. That's this right here. Isn't this v squared? That's why I didn't do the last step of v is the square root of gr, because you would just end up turn around squaring it anyway, right? Can I substitute that right there? All right. Let's take a next line, right? This is something you guys would have to be able to figure out yourself. I mean, this would be maybe a little bit more on the challenging end of an FRQ, but if you could ask this, right? I think it would be within the realm of reason, right? And then, oh look, we got M's, G's, and R's all over the place. Well, okay, I guess this one has H and these two terms have R, but I see a bunch of M's and G's. Do you guys think the M's and the G's are going to cancel? Yeah, I see 3 terms, and every single one of them has the M and the G. So at some point, I forget where I canceled it on this paper, but at some point it's got to cancel. What that means, remember when something cancels in physics, it doesn't matter how massive this is. So you could have an empty car, and you could have lots of passengers, and the geometry is going to be the same, right? Like the total height has to be the same. Also, the fact that gravity field cancels out. Whatever the solution ends up being to this, whatever got covered here, could you take this whole system straight to the moon, and the answer would also be the same? The geometry would be the same on the moon? Yeah, because the gravity field ends up canceling out. So you need gravity, but once you have it, it doesn't matter what the magnitude of it is. Right?
so the roller coaster will work on the moon?
Yeah, roller coaster would work on the moon. Yeah, so, all right, algebra. Okay, and then, okay, I guess I could save the MG cancel for the very end, but there you go. All right, this is a really classic physics question. If you guys take physics in college, pretty sure you're going to see this question, because this is a really classic question. Okay? So the minimum height, like the theoretical minimum, ends up being 2.5 times the radius. So here's 1, 2, and if you take a half and stack that on top, then straight over, right? So if you had 0 frictional loss, you'd have to start from at least this height. Like this would be like the theoretical minimum height, like right about here. Okay? And anything beyond that just makes it even safer. Okay? Good, because realistically you have some frictional loss. Right? All right, you guys ready for today's stuff? Yeah. Yeah, I think I got that one hanging up somewhere. Is it this one right here? I think.
Oh, yeah.
All right, there you go. So, yeah, I got this one hanging on the class right here. All right, let's go to today's stuff. All right, so you guys are trying to figure out what's the maximum speed of the pendulum, which would be at the bottom, right? Because it speeds up on the way down and slows down on the way up. So it goes potential, kinetic, right? So this maximum speed. You guys saw a similar type scenario a few weeks ago. There was how your textbook phrased it, like an adventurous archaeologist was swinging on a vine, and they told you what the speed was, and they were asking what's the tension in the vine, right? So we're going to go the extra step today and say, well, how do you figure out what is the speed down at the bottom? And you can figure out from the geometry. It depends, like how long is the vine, what's this angle, and also what gravity field you're in. I guess you can just figure out, right? Okay. So here's your conservation of energy setup. Guys, what kind of energy right here? Potential energy, MGH. Right now, if you start from rest, that's all there is. Right? And then energy down here is 1/2 mv squared. So that looks a lot like the Galileo setup. You guys remember Galileo dropping bombs? And the speed was square root 2gh, which is also what this is. Look at that. Speed is square root 2g, and then all this stuff represents the height change. Now, for the pendulum, it's maybe extra fun because you get to do some geometry. So, okay, I got this triangle, this leg of this right triangle is L cosine theta. This height change is L minus L cosine theta. Boom, there you go. If you like, you can factor out the L. Okay, that's what I can start. Okay. Question for you guys. Okay, well, I got the answer covered up. Suppose instead of going from rest, what if you pushed off? You guys tell me here. I'll give you guys multiple choice: A, B. Okay. If you push off rather than release from rest, is the speed at the bottom? I call it speed at the bottom. Right? Is equal to your push off speed plus square root 2gh, or is it equal to the square root of the push off speed squared plus 2gh? Right? One of those is correct and one of those is incorrect. Show of hands. How many guys say A? How many guys say B? Oh yeah, you guys are following. You guys are on. B is the correct answer. Right? You could show that with all the algebra steps I skipped from here to here. But yeah, right, that's what that would be. Say that light gray ink. Right. All right. So let's make a table here. If you guys got some paper out, we're gonna make a table. Okay. Yeah. So lab time. Let's call this pendulum speed lab. Write your name on your paper. So know who to give the points to. And let's just make a bunch of columns. Let's see, 2, 3, 4, 5, 6. So I think that should be plenty of columns. Like I've got 7 columns here. Okay. So let's go. Let me make a units row also. So we got variables and units. Okay. So we got different trials going on. Now I did make a table here, but I left off some things maybe I want to put back here. Okay. Like I didn't put mass here, but I guess if you're really meticulous scientist, you should keep track of like what's the mass of the bob, what's the mass in like grams or kilograms, up to you. Okay. The reason I didn't put it in this table is because see it can't like I have in here, but then it cancels out by the end. So theoretically it shouldn't matter. But you know, if you're a scientist, maybe you want to keep track, just make sure, right? If this was an AP question, you would not say you would use a scale because you would be expected to know that mass would cancel out, so you don't actually have to have a scale. But you know, we got what's the length of the string, the length of the pendulum? You can do centimeters or meters. I might want to stick to meters, might be safer, so that if you're mixing mass and units, like with the gravity field, oh, that might be a good thing to know too. Maybe gravity field is like 9.8 or 10 meters per second squared. Right? Maybe that could be its column, or you could just kind of know that off the side. What is the starting angle from the vertical, and like how many degrees would that be? Right, and then let's have 2 different columns for speed, final speed. Right, so one final speed, so units meters per second, right, could be empirical, right, and that is using a speed gate. Do you guys think you can take the speed gate? Everybody has one of these at their desk, right? Dunk it upside down and let the pendulum fly through it, and it can tell you exactly how fast it's going. Right? That's a little tricky. Sometimes you can try it like 3 or 4 times, it doesn't register, and then you try it like 5th time, it's like, okay, now I got a number. Okay, so I have to do a few times. Okay. Okay. And then the other way we're gonna do final speed is calculated. Okay. And that is that's this right here. Right? So let's go equals square root of 2gl 1 minus cosine theta. Right? Yeah, you should be able to derive that from scratch, right? Right? Like, guys, every one of these posters, the more of these posters that you like take to heart and are able to like do yourselves, like independently, if you say, I'm gonna break out a blank piece of paper and like solve this from scratch, right? Like the more prepared you're gonna be for this AP exam. Like I've seen plenty of AP exams over the years, so no stuff you need to know. This is still gonna be meters per second, right? You know, as long as everything's in meters and seconds. Right? If you stick to base SI units, it's probably a pretty safe thing to do, right? Okay. Right, you guys got that table? Okay. So you guys got title, pendulum speed lab. You guys wrote your name. Pick a value for gravity, either 9.8 or 10 meters per second squared. Right. You got trial 1, 2, 3, 4, 5. Different trials. Right. You keep a track of what's the mass of the bob, what's the length of the pendulum, what's the starting angle from the vertical. You guys all have protractors on your desk, right? So you can lift the pendulum from to some angle, say like 30 degrees. Right? And then 2 different perspectives on speed, right? What does the speed gate actually say it is? versus what does your calculation say it should have been according to conservation of energy, right? And hopefully these two numbers are pretty close to the same all the way down. Okay. Now, this is going to be kind of an exploratory lab, so I'll let you guys choose what you want as an independent variable. But you can just be all mix and match and crazy if you want. If you want to do different masses and different lengths and different angles, and just have a field day, right? Right. So when you after you do a few trials, how much time we got here? Oh, great, we got about 19 minutes. Great, that's perfect. Okay, so you guys got plenty of time to get a few trials, try this out, see how these speeds match up. Toss this in the grade tray, and I will give you points, and that will close on the week.